Salam and welcome everyone. So today we're going to be working on the question on the screen that says a sodium lamp emits yellow light at 550 nanometers. So that's the wavelength. How many photons does it emit each second if its power is 1.0 watts, as well as if its power is 100 watts? So they're first of all telling us that we have a sodium lamp that emits yellow light at a 550 nanometers. So we already know nanometers, meters, they're just basically saying that's the wavelength. So the wavelength is 550 nanometers. Now we're asked to find how many photons. So basically, the number of photons does it emit each second. So that's what we're looking for. So how many photons per second? So each second is just 1 second. If its power is 1.0 watts and 100 watts. Before I go on to solve this question, I want to quickly mention that this question is from the Atkins Physical Chemistry 11th edition, chapter 7, that deals with quantum theory, quantum mechanics, quantum chemistry. So I just wanted to know you guys to know that you should listen as much as possible so that you get all of the information, and you should be open-minded to using your intelligence to solve this question because it's not as direct, although it's very simple. So sodium lamp emits yellow light. How many photons does it emit each second if its power is this? So let's start with the first question. The power is 1.0 watts. Now, whenever you are asked to solve for how many of something, right, you have to remember that what that thing is actually asking you for is for you to write. So it was to do this, we're just going to use our normal understanding of mathematics, where if you're supposed to find like the quantity of some each individual thing, you're going to write the total number, okay, of the energy, okay, divided by the energy of each individual photon. So how many photons does it emit each second? So the number of photon is just going to be the total energy divided by the energy of each individual one. You can also cross multiply. Let me explain the concept this way as well. The total energy, okay, that is emitted at that particular wavelength will just simply be the number of the photons that were emitted times each individual energy of photon. So that is basically what this is. So when we have this, we know that we're going to basically need to determine what the energy, okay, of the photon is. So energy of each photon. And we're also supposed to determine the total energy of the photons that were emitted. So that's just basically it. So basically, so the total energy, okay, divided by the energy per photon or energy of each photon. So that's it, right? Now, I want to quickly mention this. You're going to be wondering, okay, how do we find the total energy and how do we find the energy of each photon? We know from our knowledge of physical chemistry and quantum theory that the energy of photon is just simply equal to the Planck's constant, okay, times the frequency. So we can easily substitute, right? So NP is now going to equal the bottom is just what? It's just going to be the Planck's constant multiplied by frequency. Now the top is asking what is the total energy? Well, let's go back to our question. We were told that its power is 1.0 watts. Now, if you're using your knowledge of physics that you have done, whether it's in high school or whether it's in as an elementary physics course in college or even in chemistry, you're supposed to know that generally the formula for energy can also be power times time. So the total energy that is emitted at 550 nanometers from the photons is actually going to just be the power that we're giving times time. And the unit for power is watts, okay? It can also be, the unit for power is also joules per second. So I just wanted us to write out everything because everything has to come in order for us to know what we're doing. So hence, the new formula is just going to be power times time. Okay? Power times time. Now, we go back to our question. We're given power, okay? We're given time, but and we also know what the Planck's constant is because Planck's constant is a constant. It has the value H is equal to 6.626 times 10 raised to the power of negative 34 joule seconds. So we have the Planck's constant as well. So we have power, we have time, we have Planck's constant, but we don't have the value for frequency. So we're also going to remember, and again, this knowledge builds up on multiple things in physical chemistry. It deals with your knowledge of physics, your knowledge of chemistry, and your knowledge of pre questions in this particular textbook. So now, when you want to get frequency when given wavelength, you have to use the formula C is equal to wavelength times frequency. So frequency ends up becoming the speed, okay, the velocity divided by the wavelength. So that's basically it. So we're going to rewrite this here again. NP is now going to equal PT divided by H multiplied by C divided by wavelength. Okay. So NP ends up being equal to PT, okay, divided by HC, okay, multiplied by lambda. So this is actually the full formula that is going to be necessary to solve this question. So if you have any questions, please leave it in the comment section. Now, let me just do a short recap before I start to substitute. We're told that the sodium lamp emits yellow light 550 nanometers. We're given the wavelength, okay? Then we're asked to solve how many photons does it emit. So we are asked to solve how many photons that is emitted at that particular wavelength per second. So they gave us time, and which is just each second. So that's 1 second. And they gave us the power. So now we have the power, we have the time, we have the wavelength, and we can actually solve the question now. Remember, C is speed of light. We know that if speed of light, sorry, C is speed of light. So really we have all what is necessary for us to solve this question. We have the power, the time, the wavelength, the Planck's constant, and C. So the value of C, for those of you who don't know, is just 2.998 times 10 raised to the power of 8 meter per second. So anyways, we have now that NP is equal to the power, which we know to be 1.0 watts. But then again, we're about to do a calculation. So we're going to use the SI unit of what watt is, which is just basically joule per second. So that's what watt is. So I'll just say 1.0 joule per second multiplied by time. So multiplied by 1 second multiplied by the wavelength, which is just 550 nanometer, 550 times 10 to the power of negative 9 meter, divided by Planck's constant, 6.626 times 10 raised to the power of negative 34, okay, joules seconds. So, because that's the unit for Planck's constant, 6.626 times 10 to the power of negative 4 joules seconds times 2.998 times 10 raised to the power of 8 meter per second. We already know we are scientists. We just have to cancel out the units. So we have joules here, we have joules here, we cancel out. We have meter here, we have meter here, we cancel out. We have seconds here. So from 1 second, we have seconds here, we cancel that out. And we also have seconds here, we have seconds here, we also cancel that out. So what you end up with is just NP is equal to 1.0 times 1 times 550 times 10 raised to the power of negative 9 divided by 6.626 times 10 raised to the power of negative 34 times 2.998 times 10 raised to the power of 8. So that's basically what this is. And you can see even our work is correct because we don't have any units. When you ask for the number of something, you don't put any unit for that. Like how many apples are there? You just say 5 or you say 5 apples. How many photons? Just say so number of photons each second. So that's just basically, so you can see no unit is here, right? So that is also telling you that you have not done the calculations wrong in any way, shape, or form. By God's grace. I mean, so you have, when you input this whole information here in your calculator, you end up with 2.8. Okay. Sorry. You end up with 2.768724 times 10 raised to the power of 18 photons each second. So this is how much photons are emitted. We have 2.768724 times 10 to the power of 18 photons are emitted at a wavelength of 550 nanometers each second. Now, of course, we're scientists, so we have to look at our question again and put our answer in the proper number of significant figures. We see that this one here is in 3 sig figs that were given 1 second They did not really tell us how many sig figs, but we've been given our power to be in two sig figs. So I'm going to rewrite the answer to this question. The number of protons ends up becoming 2.8 times 10 raised to the power of 18 photons each second. So this is basically the answer to the question. Yeah, that is it. That is the answer. So yeah, that's it. If you have any questions, again, put in the comment section. Now I want to go to the part two, or the second question, where we're told that the power is 1000 watts. So the second one says, to solve this, when we have 100, sorry, not 1000 watts, 100 watts. Again, let's remember the formula we're going to be using would be MP is equal to P times T times lambda divided by HC. So NP is just simply going to be P times T times lambda is equal to HC. And again, let's not forget the number of photons is going to equal to the total energy divided by the energy of each individual photon. And when you do that, you substitute the value for total energy to be P times T, and you substitute the power, sorry, it substitutes the value of each photon, changing it to equal h v, so h times the frequency. When you do that, you rearrange the formula to actually get this formula right here. The power times the time times the wavelength divided by the Planck's constant times the speed of light. So NP is now going to equal the power 100 joule per second times 1 second, because just the time, times lambda, so that's 550, times 10 raised to the power of negative 9 meters, divided by HC, which is just 6.626 times 10 raised to the power of negative 34, okay, joule second, times 2.998 times 10 raised to the power of 8 meter per second. So that's it. So let's cancel out the seconds, cancel out the seconds, cancel out the meters, cancel out the meters, cancel out seconds, cancel out seconds, cancel out joules, cancel out joules. So yeah, so NP just ends up becoming 100 times 1 times 550 times 10 raised to the power of negative 9 divided by 6.626 times 10 raised to the power of negative 34 times 2.998 times 10 raised to the power of 8. So yeah, this is it. So number of photons is equal to 2.768, okay, 724, okay, times 10 raised to the power of 20 photons. Yeah, that's it. Now, again, we are chemists and we're supposed to be putting our answer in the proper number of significant figures. So, therefore, we go back to our question. We're dealing with 100 watts now. We have 3 sig figs for 550, and we also have 3 sig figs for 100 watts. So, that means we put our final answer in 3 sig figs. Okay? Yeah. So, we put it in 3 sig figs. So, the answer becomes the number of photons emitted at 550 nanometers is 2.77 times 10 to the power of 20 photons emitted each second. So that is basically the end of this video. If you have any questions, suggestions, or concerns, please put in the comment section. If you would like to rewatch this video in order for you to improve your understanding, please do. I'm also going to be doing a very similar questions from the Atkins Physical Chemistry 11th edition textbook, so you can also check that out as well. So yeah, that's basically it. So if you would also like me to be your personal tutor, I am available and I'm taking students. I help students succeed in all their STEM related courses, whether they're in middle school, high school, or college. And if you would want a tutor to help you succeed in academia by the way of tutoring and mentorship, make sure you email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.